SwayamPrabha. Digital India. Educated India.
Okay, with particular focus on the Gaussian or the normal distribution. So this is a very critical. First of all, am I audible?
Yes, sir.
Statistics holds the key to inverse problems. As you know that because it's not that you can do some dy by dx equal to 0 and directly get it, because we have too many measurements, we have too limited parameters. There is some noise in the measurement. So there are some additional constructs we require. So there's a lot of effort required in building up a forward model, inverse model. Then there's a proposal for generating samples. It is not so straightforward like solving a differential equation or a quadratic equation or a cubic or whatever. Okay, so there's a lot of, and there is some non-uniqueness. Different people can approach it differently and so on. That's what gives flavor to this. That's what gives flavor to some this thing. Otherwise, it will be like a set pattern, right? So statistics, in fact, statistics is also the key science. Is the key driver of data science also. So you have to be good in statistics. If you look at any data science program, they'll ground you in statistics. So it's very useful to learn not only theoretical statistics, you should also learn computational statistics. Okay, computational statistics holds the key, where you're able to compute. You are able to do a lot of Monte Carlo simulations and so on. Okay, little bit we will do as a part of a Bayesian approach in this course. But anyway, let's look at the basics. So these assumptions we made in the least square regression, I can teach it later also. But since we spent so much time in one example, where there were some 6 measurements, we used a forward model, constant thermal conductivity, steady state, no heat generation, constant property, all of the properties are constant. So you got a temperature profile as linear, A plus Bx. There are more than 2 measurements. So you'll have to deal with it. So we found out what is the best line. That best line we approached it statistically. Okay, so we try to find out the deviation of the line from the respective data point and call it as R of I, residual of I, square it and sum it, sigma I equal to 1 to n. This we call it as the S, capital S, sum of the residual. Then we did dou S by dou A equal to 0, dou S by dou B equal to 0, dou S by anything equal to 0, where that anything is the parameter you want to retrieve. So finally, the whole problem becomes a problem in linear algebra. It was trivial for us, just 2 equations in 2 unknowns. It may involve some 500 equations and 500 unknowns. Then you should be a good stud in linear algebra, Gaussian elimination, matrix inversion, Gauss-Seidel method, Gauss-Jordan, all these things, LU decomposition. So you must be able to Cholesky decomposition. So many other methods are there. So linear algebra will automatically become important, particularly problems of the atmosphere and so on, problems in finance, computational finance, and all these things. But there could be several parameters you want to retrieve or recover or estimate. So there was some sigma, or the sigma I, which is the sigma squares the sigma was basically the error, right? So we made a lot of, so this is my exclamation mark. If anybody has, I've developed it over the years, so I cannot get rid of it. So don't think that is measurement T. Don't try to put an I to this, okay? So this is the error in the measurement. Okay, so we have to quantify it statistically, because it is not like some quantity which is easily known. It's not the, it is random, okay? And but we know the error is random, but we know some properties. So this is the variance. Okay, now let's keep this in the brackets. Okay, the first assumption are errors are additive. I'm going over it again because it's important. Errors are additive. Okay, so therefore your yi. Okay. So measure actual. Oh. Okay, so since this may confuse you, I will just erase this so that comes later. Huh? Let's start with this. Huh? Then this is very important. Okay, so or is called the errors of constant variance. The errors of a constant variance equal to sigma square. Now, yesterday there was Anand that raised a point. If the sigma is varying, we can deal with that. That's called a weighted least square. But for starters, we can say that there's nothing special because it's the same thermocouple which is used in all the points. Okay, and the error is expected to be the same. However, when can this assumption be challenged? For example, let us consider a slab like this. Okay, then there is a heat generation. So this is the slab. Okay, so there is a K1 of this, there is a K2 of this. All this you can qualify. L, W, W1, L1, and all this. Okay, now it is generating a lot of heat. Okay, let us say in all the four sides it is cooled by a convection. Please note that we are in inverse heat transfer, so examples will be from heat transfer. Okay, so HT infinity. The forward model for this problem is okay. So this is your the forward model is del square t equal to 0 when x, y are not in this thing, and del square t plus qv by k2 is equal to 0 when x, y are in. Okay, I'm writing it in. I'm doing what is called in Sanskrit Mishra. I'm mixing. I'm using a mathematical and non-mathematical language. It's okay, but I think the class is smart enough to understand what I'm saying. So you have to apply the Poisson equation, which is heat conduction equation with the heat generation in this domain. But outside this domain, you just apply the Laplacian equation, Laplace del square t equal to 0. then you have to use some continuity of temperature and continuity of heat flux at these four walls, so that there is no discontinuity in the temperature of the heat flux. Then we can solve it using COMSOL. You can solve it using Python R, Fortran C, ANSYS Fluent, Open Foam, what have you stuff. Okay. Now, because the temperatures are expected to be very high here, because there is a heat generation, the temperatures are lower here. Suppose we are putting thermocouples, we are measuring. Suppose we are doing some remote measurement, and this is basically for diagnostics. So something is happening, something is malfunctioning. You want to know exactly what this QV is, or you want to have an idea of the maximum temperature and so on. Since the temperatures are very high, the temperatures could be 100, 200, 300 degrees here. It could be only 50, 60, 70 degrees. For example, all these depend on the dimensions K1, K2, Q, and so on. I'm just given this is for argument's sake. In that case, the temperatures are way orders of magnitude higher than the temperatures here. Therefore, the errors with that such high temperatures could be much higher than the errors in this. Therefore, the variance with the measurements could be very high compared to the variance with the measurement here, though the same thermocouple. For example, you may use a thermocouple with the extended range, or you may use different sets of thermocouples. In that case, you cannot have a universal sigma. There could be a sigma I depending on the range of the temperatures used. That is why, in order to make the formulation general enough, okay. Now, the errors associated with different measurements are unrelated. You understand? So, epsilon j I not equal to j. Okay. So the covariance of epsilon j equal to expectation of epsilon I epsilon j equal to 0. Is it okay? So, of course, we can work further on this, because we already said somewhere that the expectation of epsilon I is itself 0. So this is 0. This is 0. Epsilon of expectation of epsilon I, epsilon j. So you can work further. You can work further on this. Okay. Okay. So you can work further on this. See, this concept is also used in turbulence, for example. Suppose you want to study the CFD of a turbulent flow. So you will just say that velocity u, let's say two velocity components, velocity u, and so this is called u velocity, v velocity. This looks dumb. Let's check flow over flat plate. This is the boundary layer. So delta is a function of x. There is something coming at u infinity, and this is the length L or whatever. Now I'm measuring with an anemometer, hot wire anemometer. So this is the velocity. U is a function of time. So at particular location. So let us say that this is V. Huh? Now you have to qualify this. So this plot is V. This plot is V. Now the way we approach the theory of turbulence is like this. The u velocity can be written as a sum of an average velocity plus a fluctuating velocity. Okay, velocity. So this is a mean. So this is a fluctuation. Okay, so the v velocity can also be written as v bar plus v dash. Now, if you take the product of u into v, uv, so this will become okay. Now, if you take a uv bar, okay, so this will be equal to u bar v bar bar plus u dash bar plus v dash bar plus u dash v dash bar. Now look at the arguments. Is a brilliant. So this what I am doing is a very high funda concept. This is basically called the Reynolds averaging. I am teaching advanced fluid mechanics. Huh? See from where we went. So we started with LSR, then we went to error, then we went to covariance, then we went to turbulence. This is not possible in a recorded lecture. If somebody gives some lecture and you see it online and what is the, I didn't even plan today, right? I have, please note that whatever I'm writing on the board was already given to you yesterday as a PowerPoint. You see the big difference now. Okay, when I use the PowerPoint, how there is a limitation for the student as well as the prof. I have to strictly follow what is there in the PowerPoint. There is no expectation, correct? I mean there is no variability. It's all set. It's a preset menu. Sambar, rasam. Now today, because I'm not using the PowerPoint, so that the chain is removed. That chain is removed, right? And now it can be free flowing. The ideas can flow freely. Now I'm able to explain covariance better, hopefully, using this. Now u dash u bar v bar bar is nothing but u. Average of the average is the average itself. Okay. Since the errors are random, u dash bar will be equal to 0. V dash bar equal to 0. But the fluctuations in the horizontal and the vertical need not be correlated. If they are correlated, then what is the point? It is not a random fluctuation. Therefore, this u dash v dash over bar, therefore, the whole funda is u dash v dash bar is not equal to 0. So, since it is not equal to 0, it is a new animal, A-N-I-M-A-L. It is a new animal which enters into this picture. Therefore, I should be able to relate it to some other quantity like the shear stress. This led to the field of turbulence modeling. This led to the field of turbulence modeling, your K epsilon model, K omega model, all those radio buttons. You just suppose some prof gives you a project. You don't see. Yeah, the problem is everybody is doing so many things. You don't go deep enough. Now you, me, all of us, we don't go deep enough. Some ANSYS fluent is there. You want to consume. You're a consumer. You go to turbulence model and put K epsilon and K omega. K omega is developed by somebody called Mentor. So it is just a button. That button is because his mentor spent all his life trying to. You don't even know. Then when some Viva comes up, you say, "No, sir, somebody used K omega mentor." They said, "You don't even know mentor." K omega. I read in somewhere that K omega works well. But did you ever find out how this K omega came? How did so many options come into the fluent? How many scientists toiled to get there? So it's all the effort. It's not that some computer is solving. There are there are scientists who spend their time in the lab with their students themselves thinking and coming to this. And then finally, it is what is coming in answers fluent is a post-process thing. If there is scientist, if there are no scientists, if there are only programmers, you will not get this. You will not have a way of handling this. This cannot be done by a computer science or a data scientist. This has to be done by a fluid mechanics professor or a fluid mechanics scientist. So please understand it. Now, if you see, instead of just looking at blindly statistics, if you use a construct of namely fluid mechanics, through this example, you can understand what covariance is. When there is a fluctuation in the u direction, you should not be able to predict the fluctuation in the v with the help of fluctuation in the u x. Then they are correlated, the covariance. Okay, then the covariance is non-zero. Okay, that means you can get a grip on the problem. If you know one, if you know the other, that means they are related. I don't know, each of these is independent, so the covariance is zero. Like that, we are saying the error in the fourth thermocouple is quite free, is independent of the error in the first thermocouple, though mu plus or it will follow the dharma of mu plus or minus 3 sigma. That means between minus 0.5 degrees centigrade to plus 0.5 degrees centigrade, it cannot be. I mean, it is likely to be between minus 0.5 and plus 0.5, but you cannot pinpoint that it will be 0.45 because it is a random quantity. That is point number one. And just because the third thermocouple at 0.35, you just because we are IITians, we are super smart, I will say that this will be 0.45. That also doesn't work. It is random, it is statistical, it is elusive, it will tease us. You cannot just put it down and say answer equal to, it won't work. That is the nature of the phenomena. That is the nature of phenomena in science, engineering. That is the nature of a human being. That is why nobody has ever figured out how the mind works fully. Okay, consciousness, this thing, functional MRI, all these things are brain project of Obama, all those are there. Okay, but because we have limit, because the number of degrees of freedom is so much, and people can get very crazy. I mean, you can also get creatively crazy or crazy otherwise. Therefore, whenever the degrees of freedom are so much, you cannot just bring it down to something because analysis or model or science is only one part. Science is only one part, and it stays there. Science has helped us to solve a lot of problems, but science is not the be all and end all. Science has not solved all the problems of mankind. All right. Now, the fifth point is okay. The fifth point is the measurement errors follow a Gaussian distribution. F of no, that's not right. Ah. Okay, so this is the famous morning 5 o'clock when I was preparing for today's class. Though I know what is the stuff, I already had a PowerPoint. I thought I should. So that's how every day we have to try for something better than what is there yesterday. Only then there'll be progress. If you think you know everything, how can you learn at all? Okay, there should be something to know, right? Okay, so this, even if somebody says I don't know, there is a knowing already there, because you know that you don't know. You are in a good position. When somebody says, I don't know, there is a knowledge of the ignorance at least. Even though there is a knowledge, there is no knowledge of the matter which you want to investigate. I don't know is a very good proposition. I don't know that I don't know is trouble. Because if you don't know that you don't know, you think you're a genius. You just don't know there are so many things which you don't know. I mean, that's the problem. So a professor is one person, an acharya, a teacher, a professor is one person, will make you know what you don't know. Okay? Once you know what you don't know, you're all smart kids. You will try to find out some things. This could be data science, this could be mechanical engineering, this could be electrical engineering, this should be some form of medicine, this could be something. Okay? But the thing is, there are so many things out there. I don't know is a good position to be in, rather than the position of I don't know that I don't know. Okay? So the basic problem in life is the don't know square problem. That is, don't know into don't know. I don't know that I don't know. Okay? This to become this, how much time will it take? And I know that I don't know what. Can you know everything? Okay? Is it possible to know everything? What is that everything? Okay, let's not get into that. Okay? So, I don't know that I don't know. I know that I don't know. I know. At least in a limited area, if you know that you know, then you can become a leader in that field. Okay. Now, so I am talking about what is called about, this is basically epistemology, the theory of knowledge. Okay. Let's get back to statistics. Okay. So now, so this is the Gaussian. This is the Gaussian. And mu equal to 0, right? Mu equal to 0 plus 3 sigma minus 3 sigma. Funda is error %99 of the time, the error is likely to be within plus or minus 3 sigma. Okay. So this is a game changer. Not the, what is a game changer? The idea proposed by Gauss that many quantities, if there are many quantities, if you distribute them, heights, income, IQ level, craziness, whatever, they are generally likely to follow. There is a mean, there is a symmetric distribution. Some people will be above, some people below, and all that. Sometimes this can be too much of an approximation. So for that, we deal with those things using extreme value statistics like Weibull distribution. There are other distributions like binomial distribution, Poisson distribution, and so on. So for large number of samples, this is what we also use for grading for large classes. There'll be a mean plus or minus 3 sigma, yes, grade A, grade B, grade, all that, right? So sometimes I don't believe in that, but for large classes, we are given some guidelines. Okay, so this is a game changer. So again, there is a controversy because Laplace proved it first. They said Laplace proved it first. There's some other French guys also tried it, and it is generally the proof. This Gaussian is attributed to Carl Gauss, 1809. Huh? You must look at the history of this. Okay, let me get back to the morning 5 o'clock. I was preparing for the class. Suddenly, I was looking at the history. So if you want to really know something, you have to get down to the history of that. Then I looked at all the PDFs available on the internet, and there was a very nice presentation by Professor Stahl. which I sent a mail to, I downloaded it and sent a mail to Rajesh Akula at 5:45 a.m. Rajesh, 99.7.
Sir.
99.7 is okay. And I just said, okay. And Rajesh posted it to you at 6:23 a.m. Correct, Rajesh?
Yes, sir.
Rajesh, when do you wake up every day? 4?
Yeah, yes, sir.
Rajesh wakes up at 3:30 in the morning, man. But he sleeps by 8:30 in the night, correct? Okay. So Rajesh is an early riser. So he gets up at 3:30 in the morning. Okay. So every day he's doing that. Then he does he works out. You do a workout, right, Rajesh, in the morning?
Morning, sir. No, sir. Evening.
Evening you do.
Yes.
Okay. So he regularly does workout and all that. Okay. So anyway, so 6:23 we sent it. Just take a look at it. It's very interesting. Whatever I sent you. Okay. Carl Gauss did it in 1809. This is also called the normal distribution. So this is also called the bell curve. And the y-axis is here f of z, f of epsilon I. And x-axis is epsilon I. Okay. So often I found that if I ask in an interview, whether it is a MS, PhD, whatever interview, what are the x and what are the ordinate and abscissa of the Gaussian distribution? Many people are stumped. They just look at me with disbelief. How can you ask that question? Everybody knows this. Okay, everybody knows it. Please tell me. Often this is not emphasized. So this is epsilon I. This is f of epsilon I. Please note that the y-axis doesn't give the probability. Probability is a different animal. It has to be integral minus of infinity to of x, f of x dx and all that. So please don't that the f of x is not the f of x is a proposal. It's a proposal for the probability. Okay. All right. So now these points are over. And now let's go to the next point. Sigma I is known. Sigma I is known. Don't ask me, sir, how do we know it? So that comes under a special field called uncertainty quantification, estimation of errors and all that. There are some standard procedures. You talk to Rajesh Akula or Suraj Kumar, they will tell you how they are estimating the sigma of their measurement process. Okay, that will be a separate lecture by itself. That comes under the subject of measurement science. Of course, suppose in our case, the forward model was t equal to a plus bx. But suppose the forward model is itself a CFD solution, which has got an error, then the sigma which is used in the inverse problem will consist of the sigma of the measurement and the sigma of the simulation put together. But if the sigma of the simulation with a high fidelity, high quality simulation is much less than the sigma of the, how do you add? You cannot simply add those two sigma. So you will have to probably do that root of sigma 1 square plus sigma 2 square whole square, or root of all that. So you have to do it in RMS fashion, that is a root mean square. So you'll have a way of doing it. Okay. So the fundamental thing is sigma I is known. Even more profound is, let us say now comes a key point. Errors are only in y and not in x. Okay. So how is it possible? How is it possible? That's the way it is done. Even if there is an error in x, you have to transport that error to error in y. That means I know the location exactly. I don't know the temperature exactly. But we have a way of you've got a theory of error propagation, and we can deal with that also. But for starters, let us assume that the error is only in the dependent variable and not in the independent variable. Okay. And the last point is pure LSR no prior knowledge of parameters is available. See, all these Laplace, Gauss, De Moivre, all those people, those classical probability theory guys. 1809 means that 212 years old. They started with this, but now Bayesian method. Okay, it was started by Thomas Bayes, which he proposed it, the Bayes theorem, long time back. But now last for 30, 40 years, I am also Bayesian. That means I believe in Bayes. So I will just say that this is not okay. I'll say that if you're an engineer, I will have prior knowledge of the parameters. So I will get a better answer. I don't believe that everybody should get there. Everybody, it is not a fair world. A smart guy should be able to get the answer better. What about the universality of science and blah blah blah? This is not science. This is engineering. Okay, smart guy will get the answer better. So be it. Okay, all right. Okay, so now, any doubts in this? So we went through some very important. Now, let's get back to the present. Okay, so from current slide. Okay, so this was we did this. Errors are additive. See, errors are additive. Errors are like this and covariance, and the only variables that contain errors are measured temperatures. No prior information. See, if you see this, as far as statistics is concerned, let's get back to the inverse problem. We should not lose track of the main story. The inverse problem. Okay, why has the inverse problem? Why was the inverse problem not touched for a long time? Okay, so this is because it comes from the basic thing in mathematics. So there are two categories of problems in mathematics called well-posed and ill-posed problem. The original definition is given by Hadamard in 1923. Okay, this everybody quotes even today. It's 100 years old. So he's the father of this terminology. Okay, first time he wrote in scientific literature. So well-posed and ill-posed. So our Guruji is Hadamard. When did he do this? 1923. What did he say? A well-posed problem has to satisfy three conditions. The solution must exist. 2, the solution must be unique. 3, the solution must be stable under small changes to the input data. I come again. For a mathematical problem to be well-posed, Hadamard in 1923 said that the problem has to satisfy the following three conditions. Solution must exist. Solution must be unique. Solution must be stable under small changes to input data. Forward problems are usually well-posed problems. What is a big deal in that conduction in a solid is a well-posed problem. Okay, solution exists. You know that the solution exists. You integrated. Solution is unique. Of course, P equal to A plus BX to boundary condition, it is unique. Solution must be stable to small changes in input data. Even if you put small changes to the input data, it won't oscillate so much. Okay, so forward problems are generally well-posed problems. For inverse problems, one is also easy to prove. You must. It's very easy for you to figure out. There can be only one thermal conductivity which causes the temperature. There can be only one, that is the uniqueness. There can be, or first it's the existential question. There must be a heat flux which causes the temperature. So therefore there should be a heat flux which causes this temperature because there is no other culprit which can cause this. There should be a cancer which caused this reading in the MRI or CT scan. There can be no other culprit. Therefore there exists a tumor. Okay, that is the inverse problem. So there exists a tumor. And there exists a thermal conductivity or heat flux, and there should be only one. Okay, that is the uniqueness. So this one uniqueness, sometimes you'll go for a 6 in inverse problem because in the atmosphere, several combinations of humidity, temperature, water vapor, ice, water ratio can lead to the same conditions in the atmosphere. So the uniqueness is some trouble. Existence is no trouble, and solution must be stable to small changes in input data. is a big problem in inverse problems. Okay, because they are very, because it is, that is why they are ill-posed. Because of the difficulties with points 2 and 3, not necessarily point 1. For long, investigators never went near inverse problems. They said that we know that there are some inverse problems, but they cannot be solved mathematically. Let us keep them aside. You can do some guesswork, you can do some engineering work, guesswork, and let's not go near them. Okay, but how did the things change? First, Professor Beck solved the re-entry problem, and then he said that there's something called, and simultaneously Tikhonov, Russian professor, they said that you can regularize instead of just taking least square plus lambda of the square of the parameter or something like that. So he said that you can regularize the function so that just don't minimize s plus something. That something will take care of large or violent changes in the parameters. It will penalize the solution from using large values of the parameters. So it will act as a sort of bounds to the parameters running wild in your search algorithm. Okay, the parameters cannot run helter and skelter. They cannot just let loose and run wild. So you'll have to bring on some shackles so that there are bounds for these parameters in when you are exploring the parameter space. Okay, so this is a regularization. So this is just regularization. It's not very old. It's just some 50 years old. After that, so personal computers came, supercomputers came, advanced programming languages came. Then software has come. For technical software has come. ANSYS Fluent, COMSOL, Star CD, OpenFOAM, all that IcePack. So many things have come. Now Bayesian approaches have come. Neural network has come. Data science has come. So if you have all this, then you have to go back and you can give a call to Hadamard and say that boss, now it is 98 years old. We know how to deal with problems 2 and 3, and so it is not like that you said in 1923. It is like this. So inverse problems are very difficult to solve. Now you can tell him that they are still difficult to solve. There are many problems which we can solve now. Okay, so I will stop the presentation. I didn't give the presentation at all, is it?
No, sir.
I see. Okay, that's okay. So this is what I spoke. So even without a slide, it's all good enough, right? According to Hadamard 1923, the solution must exist, solution must be unique, solution must be stable. Forward problems are well-posed problems. Inverse problems, 1 or 2 are easy to prove. Through 3 is always a sore thumb. Now it's okay. So without the PowerPoint also is very good. Okay, so I'll stop sharing. Any doubts in today's class?
Yes, sir. I have one doubt.
Sir,
when we are talking about covariances between two errors, there you gave an example of fluid mechanics, like fluctuation in U is related to fluctuation in V velocity. Can we have a similar example in inverse heat transfer problem? Like already you gave one example where errors can be like a standard deviation of the errors can be different. Like when we are
Adam, from yesterday you're asking what is bothering you. Tell me, you're harping on this continuously. What is bothering you?
No, sir. Actually, this covariance that we are checking, fourth point. So that covariance that we are checking, and we are telling that covariance between two errors are different, is 0. So can there be a situation where the covariance between the errors that we are measuring, like temperature we are measuring, but the covariance is non-zero?
No, covariance, it could be non-zero if they are related or something. So so that is a theoretical situation. So, but we are saying that if the covariance 0, you are safe. But you are asking me for a specific example. I will think about it and let you know. But there is no problem with this. What is a mathematical problem with this?
No, there is no mathematical problem.
Okay. Yeah. There is no mathematical. And I gave you an example in CFD also today.
Yes, sir. Yes, sir. No mathematical, practical.
There is no mathematical problem. Yes, but sir. Generally in a thermocouple, but sometimes sometimes the physics is such that if you know the signature at one place, you can automatically predict the signature in some other place. Then it is a correlated. So instead of talking about an error, okay, let me talk about a physical phenomena of a covariance or correlation. Okay, there is a fin which is losing heat. Okay, are you there, Anand?
Yes, sir, I am there, sir.
There is a fin which is losing heat. The heat is lost by both natural convection and radiation, let us say. Okay, and your inverse problem is to simultaneously get the heat transfer coefficient and emissivity. Are you getting the point? Let us say that my mobile phone is like a fin. this surface coating is black and it is losing heat by convection and radiation. I'm measuring the temperatures. I have the forward model, I have everything. It is a combined convection radiation problem. Now, if you try to recover the heat transfer coefficient and the emissivity simultaneously, that is a correlate. These are correlated parameters because a high value of emissivity, a low value of H, a lower value of emissivity, high value of H will give the same temperatures. Therefore, you have to be careful. The covariance will be, if these quantities are taken, the covariance will be non-zero. Is that okay?
Yes, sir. Yes, sir.
So this is an example of heat transfer. Okay. All right. Okay. Ujjal is still putting 5.4987 all that. Okay. Now is it fine? So let's close for the day. Tomorrow 9 o'clock we'll meet. Thank you.